Okay, so we want to start off today with a little bit of review of a circle. So we're going to pretend that looks like a circle, and we're going to look at some of the parts of a circle. First of all, the main part of a circle, what's that piece called? A radius. Very good. What is that piece called? The segment that has its endpoints on the circle? A chord. And a chord that happens to contain the center of the circle is called what? Diameter. Which brings us to our first relationship. That's between the diameter and the radius. And what is that relationship? Yeah, the diameter is equal to 2 times the radius. Wrapping around the circle, we do have the circumference. Which brings us to our second relationship. The circumference is equal to what? You're thinking area. It's either pi times diameter or circumference is equal to 2 times pi times the radius, because the diameter is 2 times the radius. So either one of those work for circumference. So those are all pieces we've seen before. In fact, there are some others that we've seen before, like if we take 2 radii, the area between those 2 radii is called what? A sector. There you go. It does kind of look like a piece of slice. The portion of the outside edge of the circle that's cut between those 2 radii is called an arc. And the size of that all is defined by, this is called the central angle. It makes sense. It's a central angle because it's at the center of the circle. The vertex is at the center of the circle. We have some formulas here that go with the sector area. To find the sector area, the first thing we need to find is the area of the circle. So A with a little circle there is the area of the circle. What's the formula for the area of a circle? This one was pi r squared. Pi times radius squared. And we showed you last semester where that formula came from. So then to find the area of a sector, that area with the little pie slice or pizza slice by it is area of the sector. It is the area of the circle times what? What's that symbol mean? Yeah, that symbol is your central angle over 360. That angle over 360 is defining what fraction of the whole circle that sector is. So that is our sector area. The arc length is defined as a piece of the circumference. It's the circumference times what? That same fraction, theta over 360. So let's put some numbers to this. If the radius here is 8 inches, and the angle here, let's call it 50 degrees. Let's find the sector area first of all. What's our first step to find the sector area? Be the area of the whole circle, which is pi times 8 squared. Pi times 8 squared is going to be what? If you use 3.14 for pi, it comes to 200.96, and 8 is in inches, so that's inches squared. That's the area of the whole circle. How do we use that to find the area of the sector? $200.96 times 50 over 360. Giving us 27.91. Is that what you had? All right. So 27.91 square inches is that sector area. How about then the arc length? What's the first step in finding the arc length? The circumference, which is going to be found by doing what? Is it pi times 8? Why is the 2 there? Perfect. The 8 is the radius, so we have to double it to get the diameter, which ends up being 50.24 inches is that circumference. How do we get the arc length from that? Okay. So 50.24 inches times 50 over 360, which is going to give us 6.97, works for me. Inches is our arc length. That look familiar? Okay. So we have that inscribed angle right here. Or sorry, that's called the central angle, I should say. Which defines that arc or that sector. Well, there's another angle we can create that might look like this. Instead of the vertex of the angle being at the center of the circle, the vertex of the angle is on the circle, on the outer edge of the circle. That type of an angle is called an inscribed angle. Inscribed means it has its vertices on the circle. We can have an inscribed angle like this, so it only has one vertex, so the vertex is on the circle. We can actually inscribe polygons like we talked about last week. We can take a hexagon and put all of its vertices on the circle. That'd be an inscribed hexagon. Other features we want to make sure that we understand. When we had that chord, the area between the chord and the outside edge of the circle is called what? Anybody remember? Segment. That is a segment. Now, if you recall from last semester, the way we found the area of a segment, we had to find the area of the whole sector and then subtract out this triangle to get what was left. You couldn't calculate the area of the segment directly. Let's go to another circle. Some more features. If I have a line that touches the circle in exactly one point, but never actually goes into the circle, that line is called what? A tangent. A tangent has a lot of significant consequences to our circles if we start to do applied problems with them. One of those consequences is if we have a radius of the circle to that point of tangency, they always form a right angle. Since we're going to be talking about trig in next week or so, finding right angles is a big deal. That's one of the spots where we find right angles. Next, we have a line like this, a line or a segment that contains points both inside and outside the circle. That is called a secant. Now, we've already talked about diameters. There's a special diameter we want to talk about that's horizontal like this. That is called a reference diameter. It Can be, but usually we use either a horizontal or a vertical diameter as a reference diameter. Yes, but the horizontal reference diameter is our main reference diameter when we're talking about trig. The vertical is going to be is called the co-reference diameter, but we'll get to that in a few hours. If I pick any point on this circle, like I pick that point there, a feature of that point combined with our horizontal reference diameter is something called the sine. The sine is the distance from that point to the reference diameter. So notice that point has a sine. This point has a different sine because it's closer to the reference diameter. This point here has the biggest sine because it's the furthest away. So every point has a sine. So as we start talking about these angles and all that stuff on the circle, we're going to talk about something very special circle. It's called the unit circle. The unit circle is called the unit circle because the radius of this circle is equal to 1 unit. Now we are going to work with this unit circle a lot over the next several weeks. So on this unit circle, it sits on a grid, and the center of the grid is also the center of the circle. The right direction, what would be, we would consider the positive x direction on a regular grid, is 0 degrees. And we go around it going counterclockwise. So this is 90 degrees up here, 180 degrees, 270 degrees, and then 360 degrees is back at 0. Now you can keep going around. I mean, this would be, now 450 and 540, and you can keep going. But once you've gone around once, there really isn't a whole lot of point of continuing to go. The only time you really go past 360 degrees is if you're getting into like motors, tracking motors and phases, or electrical impulses and stuff like that, where they continue to cycle over and over again. So you need to repeat that cycle. But anyway, this 0 degree mark is what is referred to as the initial side of an angle. That's where all angles start. And our angles, as you can see by the labeling, go counterclockwise. So let's say that is 50 degrees. So now that 50-degree angle traces out a lot of things on our circle. It gives us this point here for one. Now that point would have a sine, which we'll talk about later. But for right now, what we're concerned about is that point as we rotated from the initial side to that side, which is called the terminal side. Terminal side is where the angle stops, of course. It traces out an arc length here. What is the length of that arc? Well, what is the circumference of that circle? It's 2 times pi times, what's the radius? 1, right? So the circumference of that circle is just 2 pi. So that arc length is 2 pi times 50 over 360. I'm going to do this. I'm going to put the 2 pi over 1. I'm going to divide out a 10 here. The 5 and the 50 and the 360 are going to become 5 and 36. So 2 pi times 5 is 10 pi. 1 times 36 is 36. Now that can still be reduced. Both 10 and 36 can be divided by 2, gives me 5 pi over 18. The length of that arc length on the unit circle is defined to be the radian equivalent of that angle. In this case, it's a 50-degree angle. So what that is saying is 50 degrees, a 50-degree angle is equivalent to saying that is 5 pi over 18 radians. And that's just an alternative way of measuring angles, is measuring them in radians rather than degrees. The difference is very subtle. Degrees measure rotation. 50 degrees means that's 53/60ths of a full circle. The 5 pi over 18 radians is literally just the length of this arc that angle forms on the unit circle, a circle with radius of 1. Well, if an angle were to go all the way around here, how many degrees would that be? That'd be 360 degrees. What would the arc length be all the way around here? 2 pi, it's the circumference of the circle. So what that's telling me is 360 degrees is equal to 2 pi radians. Yeah, it's just the, oh sure, they just said that 180 degrees equals pi and you use that as your conversion. Yeah. So to convert angles, we can use that equivalency. Now, like I said, a lot of textbooks use 180 degrees equals pi. They're just dividing out the 2. I usually leave it as 360 equals 2 pi just because I know where that comes from, so it's easy for me to remember. But if I want to convert, let's say you asked to convert 120 degrees to radians. Well, I'm going to take my 120 degrees. I'm going to put it over 1 to make it a fraction. And then I'm going to multiply by a conversion factor, just like we do with the measurement. Degrees are going to go on bottom so that they cancel out. Radians on top. 360 degrees equals 2 pi radians. So now the degrees cancel out. I'm just going to multiply it out. 120 times 2 pi is 240 pi. 1 times 360 is 360. And of course, there's radians here. And then I can reduce this. Both 240 and 360 divide by 120. So that's 2 pi over 3 radians. What's that? Yes, that's a standard one. Yeah. Let's say I have 3 pi over 4 radians, and I want to convert that into degrees. Well, we're going to do this. We're going to take the 3 pi over 4, and I'm going to put the radians up in the numerator. Because most of the time our radians are given as a fraction, I don't have to put it over 1. I can just use the fraction form that's already there. Now in my conversion factor, where are radians going to go? Bottom, so they cancel out. So degrees will go on top. 360 degrees is 2 pi radians. Now 2 things happen here. First is the radians cancel out. Second is, in many cases, the pi will cancel out. So now we just have 3 times 360, which is 1,080 degrees. 4 times 2 is 8. So 1,080 divided by 8 is 135 degrees. So that 3 pi over 4 radians is equivalent to 135 degrees. What do you think? Not terrible? Or maybe you guys try a couple in your notes. So I'm going to have you convert 45 degrees to radians. And then I'm going to have you convert pi over 2 radians, 2 degrees. I'll give you a minute. So for the first one here, we're converting 45 degrees into radians. So make that 45 degrees over 1. In our conversion factor, degrees go on bottom, radians on top. 360 degrees equals 2 pi radians. So the degrees cancel out. We have 45 times 2 pi radians. Well, 45 times 2 is 90, and then pi radians. 1 times 360 is 360. Both 90 and 360 can divide by 90. 90 divided by 90 is 1, so that's just 1 pi radians or pi radians. 360 divided by 90 is 4, so that's pi radians over 4 or pi over 4 radians. How many of you had that one right? Anybody have questions on how we did that? Okay. Now for the next one here, pi over 2 radians going into degrees. Now just like we did here, we move the radians from the numerator out of the fraction. We're going to go the other way. We're going to put radians into the numerator. So pi over 2 radians is going to become pi radians over 2. That's already a fraction, so we don't have to put it over 1 like we did over here. So now we're going to get rid of radians, so they go on bottom, degrees on top. 360 degrees equals 2 pi radians. Now the radians cancel, but we also have a pi that cancels. So now this is just nothing, or 1 times 360 degrees is 360 degrees. 2 times 2 is 4. 360 degrees divided by 4 is 90 degrees. Any questions? I'm going to let you guys work for about 10 minutes here. And we'll take our break. On page 533, exercise 25-1. There's only problems 1 through 4, so you just do all of those, identifying parts of the circle. Then page 537 through 539, exercise 25-4. And I'll have you do 1 through 3 and 5 through 15. So let you guys have the next 10 minutes to work on those. So we've looked at these parts of the circles. We've converted the angles into radians. Now let's look at how some of these pieces interact with each other. Okay, so we've talked about arcs and chords. Let's say I have an arc on this circle. Make it a little bit bigger. And let's say that this arc is 13 inches long. And this chord across here, let's say that chord is 11.5 inches long. If there's another chord in this circle, let's say over here, if that chord is 11.5 inches long, what can we say about this arc? It's also 13. If they're in the same circle, or if they're in 2 circles with the same radius, 2 circles with the same radius are essentially the same circle, right? Equal chords will define equal arcs. That one is not near as important as this next piece. If we have central angles, let's say this central angle here is 40 degrees. And that central angle cuts an arc of 18 inches. If I construct another central angle here, and that central angle is 40 degrees, what can I say about this arc? It's also 18 inches. If the central angles are the same, the arcs they create are also the same. If we have 2 circles with the same radius, that'll be true between circles as well. To the point where not only are they the same? But what we start to do is define the arcs by their central angle. Instead of defining that as 18 inches, we'll just define that arc as being a 40-degree arc. So that once we know what the radius is, we can calculate the length of that arc rather quickly. So we have several 40-degree arcs. Now with that in mind, if I construct an angle here that's, let's say this one is 80 degrees, that would make this arc right here how many degrees? 80 degrees. The length of that arc would be double of the 40-degree arc within the same circle. So that'd be a 36-inch arc. Okay? So the ratio of the arc lengths can be thought of as the ratio as the degree measurement of the arc. And that degree measurement of the arc is always defined by that central angle, the angle with its vertex at the center of the circle. Which is bigger, arc A? Let's actually define it this way. I'll define it. Arc AB or arc CD? Which is bigger? Why is CD bigger? Bigger central angle. This one is only 70 degrees. Remember that 70 degrees means that's 73/60ths of the whole circumference. This one is 80 degrees. I purposely, drew the circle a little lopsided so that that other one looked bigger, but it's still the central angle defines the number of the degrees. What if instead of a central angle, let's say we got this angle here that's 40 degrees. What if instead of a central angle, we want to define that arc with an inscribed angle? So this arc here is a 40-degree arc because it's off that 40-degree central angle. An inscribed angle, of course, would have its vertex on the circle. Now I'm drawing this in a special way so that the one side is a diameter of the circle. The reason that's important is now I know that this length and this length are the same. They're both radii. That's the center of the circle. If those are both radii, what does that tell us about this angle and this angle? They're the same. This angle is going to be 140, the complement of the 40, or the supplement of the 40. That's the straight line. These two angles are each going to be 20 degrees, half of the 40. In fact, that inscribed angle compares to that central angle no matter where I do it. I can do it here where the sides are not, none of the sides are diameters or anything like that. This angle here is still 20 degrees. The measurement of that inscribed angle is half of the measurement of what is called the intercepted arc. So a 20-degree inscribed angle intercepts an arc of 40 degrees. So in this circle here, if this angle here is 30 degrees, what's this angle right here? Perfect, because this intercepted arc here has to be 60 degrees, twice that inscribed angle. Well, this is a central angle, assuming that's the center of the circle. That central angle is equal to the arc. I can do it like this. That angle is still 30 degrees. Or here, that angle, I actually intersected at that's 30 degrees, no matter where that hits. In fact, I can even do this. An inscribed angle is any angle with a vertex on the circle. I can do this. I can cut this across here and draw a tangent through here. That angle still has its vertex on the circle. This angle here is still 30 degrees, still half of that intercepted arc. I mean, you could actually do the math behind that if you wanted to, because this is a right angle, because the radius always forms a right angle to the tangent. If this is 60 degrees here, these each have to be 60 degrees because there's 120 degrees left over, and because of those radii, those two angles have to be equal. So that leaves 30 degrees there with the right angle. So you can actually prove it that way as well. Another important feature of our circle. Let's say I have a chord, and I've got a radius of my circle that crosses that chord. If that radius hits the chord at a right angle, let's look at what that shows us. Well, if I can connect the center, if I draw the radius in, by the way, the other radii in to the ends of the chord. Of course, if this is a right angle, what's that tell us about this angle? It's a right angle. This length, of course, is equal to that length, isn't it? This length has to be equal to itself, doesn't it? Bless you. So we have a right triangle where two of the three sides are equal. Well, since it's a right triangle, we know a squared plus b squared equals c squared, which means the third sides have to be equal. Right? So when we have that radius that comes in and hits that chord at a right angle, it splits that chord into two equal pieces. It also forms two equal angles here for the radii that connect to the ends of that chord. Is the opposite true? If I have a chord and I bring the radius in so that it cuts the chord in half, so that this piece is equal to this piece, well, we'll have this piece, of course, is equal to this one because they're radii. This piece is equal to itself, isn't it? So we have all three sides of the triangles are equal, which means the two triangles are congruent. So what that means is this angle and this angle are equal, aren't they? But they are supplementary because they add up to a straight line. So the only thing they can be is 90 degrees. So yes, if that radius hits that chord so that it cuts it in half, it has to be perpendicular, form a right angle with it. That's another tool. When we talk about trig, one of the big things we need to be able to do is find right angles. That's our second tool. Remember, the first tool was if you have a circle with a tangent, that radius is always going to form a right angle with a tangent. That's our first tool for finding right angles. The second is this one. A radius that cuts a chord in half is also going to form a right angle with it. Yeah, let's make this bigger. Let's talk a little bit about these tangents. So we have two tangents here that intersect outside of the circle. But we know if we draw in the radii from the center of the circle to that point of tangency, they're going to form right angles. We know that the radius is equal to the other, they're equal to each other. If I connect across here again, that green line, of course, is equal to itself, isn't it? So once again, I have two sides of right triangles that are equal, which means the third sides are equal. So that's one of the first consequences here, is these two tangent lengths are going to be the same if they intersect outside the circle. Second consequence, these two angles are going to be complementary, aren't they? This angle is going to be the same as that one. This angle is going to be the same as that one. Now, by the way, if these two are complementary, what does that mean about all four of them put together? They're supplementary. So this angle and this angle are supplementary. Here's one we actually talked about a little bit last semester. If we have two chords that intersect inside the circle, like this, the way it divides up the pieces of those chords is very unique. Let's say that this chord here is divided into pieces of 3 and 12. This other chord, let's say I know that this piece is 4 units. Can I find this other piece? Do you guys remember the rule from last semester? The two pieces multiply to be equal. So this chord is 3 and 12. So I have 3 times 12. The other chord is 4, and I'll call this x. 3 times 12 has to equal 4 times x. 3 times 12 is 36. Divided by 4, x equals 9. The two pieces with two chords intersect, the resulting pieces of the chords multiply the same number. There don't have to be similar chords. They're not the same length because this other one, one's 15 and one's 13 units long. Just any two chords within the same circle, when they intersect, the product of their lengths will be the same for the two chords. The application in construction where that's important, this is the one we looked at last semester, is if you're doing an arch. An arch is a segment of a circle. So let's say you're doing an arch that's 48 inches wide, and it's going to be, let's go 8 inches tall. In order to lay that out, it would be nice if I can find the center of a circle and its radius and just use a string and a pencil to trace that out so I can cut it out. To find the radius of the circle that creates that arc, I can do this. I'm going to take this and I'm going to go all the way down to create a full diameter. I'm going to call this length here x. That is a diameter, or this part here, of course, from here up to the top is a radius, and it's cutting that chord at a right angle, isn't it? Which means if it hits it at a right angle, it's cutting it in half. So this piece will be 24 inches, and this piece will be 24 inches. So we know 24 times 24 has to equal 8 times x. Well, 24 times 24 is 576 equals 8x. If I divide by 8, what do I get there? 72 equals x. So x is 72 inches. The diameter of this circle then is what? (72 plus 8 is 80 inches. So the radius, that's a 40-inch radius circle. So I can use that then to find the center. What I would do is I just take a circle or a string, and tie a pencil on it, and then at 40 inches tie a knot in it so I can put a tack or something through it. And I'd put the tack at one end of my arch and strike an arc with that circle. Put the tack then at the other end and strike an arc. That tells me where the center of my circle has to be. So I turn around and I'll put my tack there and use the pencil to trace out that arch. For the top of your little clocks, and the same, arched doorways between rooms. I've seen it used arched fireplaces. More and more people want to have the decorative windows, so they got the decorative arches above windows. So you've got a frame for those. A lot of times they'll just put the header up above, and then once they put the window in, they'll frame around it. They'll put tack in 2x4s to hold the sheetrock and stuff. Yeah. So let's say we have like a 60-inch wide doorway, and our arch here is only 4 inches, like that. So of course the rest of the circle is huge. So we're going to squash it a little bit because we don't have room to draw it, right? But pretend that looks like a circle. We're still going to find this dimension here is still x. This still gets cut in half, so each of these pieces is 30. So we've got 30 times 30 equals 4 times x. 30 times 30 is 900. Divide by 4, 225 equals x. So x is 225, which means the diameter, 225 plus 4, is 229 inches. So the radius is 114.5 inches. Does that make sense? You look confused. Where'd I lose you? Yeah, this is one, most of them I can show you and they make sense. This one would take a while to show you the proof behind why it has to be true. Yep. So let's say I move it up here. So it's exactly half of the length, right? So that's only 15 here and 15 here. Well, then that means it changes. This length is going to change to be smaller than the 4 inches, obviously. But this is still going to stay the same. This is what we did towards the end of last semester. We did the fireplace arches and stuff like that. It comes off of this idea here. This length all the way out to the edge of the circle, and this length are the same. So you can connect these. Those two lengths are the same because these angles have to be the same. Connect this out. Of course, that's the same as the blue. That's also a radius. These two have to be the same. And you go through with the similar triangles. Like I said, it gets kind of in depth. If you really want to know, let me know and I can go through it with you sometime. But okay, so So if that angle there is 84 degrees, what's this angle have to be? Assuming this is the center of the circle. This is a diameter. Nope. Remember that central angle cuts this arc. What's the degrees of that arc going to be? 84 degrees. So that has to be 42. That's an inscribed angle. Off an 84-degree arc, the inscribed angle is half of the arc. Now I want to talk about this angle and this angle. What they're going to do. We know that this angle here has to be 96 degrees, right? Makes that angle 96 degrees. This arc over here has to be 108 degrees. So now the big question is why? Well, let's look at a circle here. If this is the center of the circle and I have two diameters like that, let's say this angle here, let's call that 30 degrees. So this one is 30 degrees. That makes this arc 30 and this arc 30. If I look at this invisible line across here, it cuts through the center of those arcs. If I move one of the diameters, let's say I go this way like this, so it stays parallel. Try to make it look parallel. What's this angle here? Still 30. This angle, still 30. What can I say about the length of this arc here and the length of this arc here? They should be the same. So what I gained here and what I lost here are the same, which means the total between this arc and this arc still has to be 60, right? The total is 60. So when we're looking at this type of situation where we have intersecting chords, the sum of these two angles, which they're the same angle, so double that angle, has to equal the sum of the arcs. So if I look over here, the way we really work that is we add the two arcs together. So 108 plus 84, and then we divide it by 2. So 108 plus 84 is 192, divided by 2 is 96 degrees, which is what that angle is. No matter where we move this intersection, as long as we keep that angle at 30 degrees, the sum of those two arcs is always going to be double that angle. It's going to be 60. So if I have, where this angle here is 60 degrees, if I tell you this arc here is 20 degrees, what's this arc here have to be? 100 degrees. How did I get that? Yeah, the sum of the two arcs has to be double the angle. 60 times 2 is 120. Going the other direction, let's say I'm looking for this angle, and you're told that this arc here is 30 degrees, and this arc here is 70 degrees. What's that angle have to be? 50, because we just add them together. 70 plus 30 divided by 2. 70 plus 30 is 100, divided by 2 is 50 degrees. Simple enough? So now let's take a look at a little bit of a progression here. Let's say that I have an arc here that is, let's go 70 degrees. What does that tell us about this central angle here? Yeah, this is the center of the circle. 70 degrees. The central angle is equal to the degrees of the arc. What's this inscribed angle have to be? 35. Half of the inscribed arc, or the intercepted arc. What can we say about this angle here? Is it bigger or smaller than 35? It's smaller than 35. How about this angle here compared to the purple one? It's smaller yet. Notice the size of this arc here hasn't changed. They're all on that 70-degree arc. What has changed is the size of the arc on this side, on the back side, right? This was a smaller arc. Well, this one had the inscribed angle, the 35 degree. The green one had no arc there because its vertex was there. This one had a small arc there. It was smaller than the 35. This one, even a bigger arc, it was smaller than the purple one. The way it ends up working out is that angle is found by taking the large arc, the 70 degrees, and subtracting. Let's say that this arc here was 20 degrees. This purple angle would be 70 minus 20 divided by 2. Well, 70 minus 20 is 50 divided by 2 would make that 25 degrees. Let's say that this arc from here to here is, let's just call it 30 degrees. So this angle here would be 70 minus 30 over 2. 70 minus 30 is 40, divided by 2 would be 20 degrees. So those angles, now notice, what are these lines called here? This red line would be called a secant. It has points both inside the circle and outside the circle. Those intersecting secants, the angle is found by being half the difference of the two angles. So now we can look at a problem like this. Find this angle right here. Anybody have any ideas? Do you know this angle, this arc? 20. With that, can I find this arc? If I call that x, I know that x minus 20 divided by 2 has to equal what? The 25. Yes, I'm looking at these two secants. Remember, this angle is half the difference of those two arcs. So x minus 20 divided by 2 has to equal that 25 degrees. So you multiply by 2, x minus 20 equals 50. That's after times 2. Then you add the 20. So yes, x equals 70 degrees. So this is a 70-degree arc here, which makes this green one what? 35. It's inscribed, so it's half of whatever the arc is that it intercepts. What would, I got to figure out how to make this tasteful. If I draw this across here, and if I tell you that this arc right here is 15 degrees, can we find this angle? How? $83. I can find this angle. How would I find that angle? Well, we have the 15 and the 70 divided by 2. There you go. 70 plus 15 over 2, that's 85 over 2, makes that 42.5 degrees. What does that do for us? Do I know this arc here? This purple one? Sure, how do I know that? This is the diameter across here, isn't it? So this whole thing has to be what? 180. So that has to be 110 degrees because it's 70 there. Obviously not drawn to scale. Yeah. So we have that arc. We know that this whole thing from here to here has to be 145, which makes this angle 145. What else do we know? What about this angle here? So 17.5 degrees. We're at a point here we can't find that. We need to know how this arc here divides up. Without knowing more about how that arc divides up, we can't find those angles. Okay, I'm going to turn you guys loose on some homework here. It's going to be like 4 more pages. So on the big book yet, page 542 through 544, exercise 25-7, page 546 to 548, exercise 25-10, page 550 to 552, exercise 25-13, and page 557 to 560, exercise 25-17. I will warn you, tomorrow will be a quiz on these circles. Yes. That quiz might look similar to a problem like this. So you'll need to be able to piece all these things together.